Yeah, right. Okay.
So finally we approached the finish line. For this school, the last public lecture was given by Professor Amanda Cooper-Sarkar from Oxford University. It is very nice that you are here and with us, and thank you very much for agreeing to come and to give this lecture. Please join me to welcome very warmly Professor Amanda Cooper-Sarkar from Oxford University. As you see and know, she also represents the power of women in science. This is another point. Please.
Yes. Well, okay, so when I heard about this, I was told it was a topical seminar rather than a public lecture. So it's at the level whereby, I mean, I could give a talk like this at CERN to people working on the Large Hadron Collider who aren't particularly experts in parton distribution functions, but who nevertheless think about collider physics a lot. Now, fortunately for you, I think pretty well everyone here was already in the 4 lectures, so you have the background to understand this now. So, okay, as of today, right, it has become the case that the uncertainties on our knowledge of the parton distribution functions are now a major contributor to the background for any new discovery physics, right? And this happens in 2 distinct ways, right? If you're going for beyond standard model particles at high scale, you are limited by how well we know the parton uncertainties at high x, the highest fractional momentum that the quark can take. And this is the region where we know parton distributions less well, right? But ironically, it's also the case that in the region where we know them best, which is around x of 10 to the minus 2, where we already know them best, we really need to know them better, because now that we haven't discovered any new, well, so far haven't discovered any new physics at high scale, what we're starting to do is make really precision measurements on standard model parameters like the mass of the W and the weak mixing angle, real precision measurements in the hope that when we make them precise, we will see some discrepancies from standard model values, and that in itself will be a pointer to beyond standard model physics. But these quantities are measured in exactly the region where we already know things best, so we've got to do better, right? So partly explore how we can do better. And I mean, as an aside, really, it's also the case that the uncertainties on PDFs dominate the Higgs cross-section. The largest contributor to the Higgs cross-section is through the glue-glue, and that, again, we know least. So in thinking about whether you have or don't have a standard model Higgs, this is also an issue. Now, you all already saw this slide at the beginning of the pedagogical lectures, but for completeness' sake, we should run through it again, right? That any cross-section you are trying to measure at all is calculated as a convolution of the hard sub-process cross-section with the parton densities, because it's actually the partons which are doing the interaction. And this plot is the kinematic plane showing us what we are probing at the collider, where q squared is the scale of the process. It's essentially the invariant mass squared of the product of this sub-process here. And x is how deeply we're probing the fractional momentum of the struck partons. Now, I've already explained the meaning of the lines on this plot to you, and I'm not going to do that again now, but this gives you the range. Say, if you're producing things around 100 GeV, this is the range over which we can detect them, and it runs from quite high x, above 0.1, to quite low x, below 10 to the minus 4. So, you know, we need to know the partons across that kind of range. If we actually want to see something up at high scale here, we need to know them at very high x. So that gives you the picture of what we need to know. Now, we spent all those pedagogical lectures learning about how we determine parton distributions. We'll now just take that for granted and look at what the products are. So this is a fairly complete range of flavors, right? We have the U valence here, D valence, gluon, U in the C, D in the C, and strangeness in the C, all plotted at a scale of, Q squared is 10 GeV squared there, from x's of 10 to the minus 4 to 1, a typical range that we access at the collider. And you can see this has just got 3 of the main PDFs on, the Durham group, the CTEC group, and the newer neural net PDFs. And you can see how well they do or don't agree with each other looking at this plot. And you can see there are some regions where, things are going, differences can be quite significant. It's actually more obvious. I mean, that gives you the actual distributions. The differences are more obvious if we take ratios. Take everything, all of them, in ratio to the central values of the MMHT, and you can start to see where things are going off for each type of parton, right? You can see in particular we know very little about the strange parton. We're not bad in the middling region on the glue or on some of the C, but things are far from being perfect. Now, why is it that these things differ from each other, and can we do anything about it, right? I said this, I think, in the morning lecture. They differ in the cuts that they apply to remain in the kinematic region where the theory that we're applying is correct. They differ on the forms of parameterization that they use to begin the parameterization at the starting scale for Q-squared evolution. They differ on that choice. They make slightly different assumptions about the flavor structures of the C and the valence in some cases, and they certainly make different assumptions as to the heavy flavor schemes they're using and the heavy masses. And last but certainly not least of the problems, they sometimes also use differing values of alpha S from each other. Now, that is a problem that we have almost solved now. We've more or less got an accord that everybody is going to use 0.118. And it's taken a long time to get to that level of agreement that people would all say, yes, we agree, this is the value that we're going to use in order to compare to each other. They also differ in how they evaluate their uncertainties. As I said this morning, sometimes it is included the variations of your model and parameterization assumptions. Sometimes instead of that, you use an inflated chi-squared tolerance, which allows for different qualities of fits to different data sets. And if you do inflate your chi-squared tolerance, it does tend to then cover things like these model and parameterization variations, right? But that is, understanding exactly how the error is done is a lecture in itself, which incidentally I have been invited to give in CERN in the autumn term. It's a talk just about the uncertainties and how they're determined in different ways. Okay. Now, why does all this matter for physics at the LHC? Well, the best way to look at the comparison for the LHC is to calculate the parton luminosity. This is the convolution of parton in one way and parton in the other way, without you then convoluting that with a sub-process cross-section. You're just looking at how the luminosity differs. And F is a general notation for partons, so in this case it's the gluon-gluon luminosity. These would both be glue-glue. And in this case it's the quark-antiquark, so this would be Q bar, and technically you also have to take it into account the other way around, Q bar on Q, because you've got two identical things coming from either side. Now, if we look at this for the 3 main PDF fitters, you can see around about the mass of the Higgs here, they really managed to coincide quite nicely. I wondered to some extent, Sabir was talking about confirmation bias. And sometimes we get this in all fields, the feeling that we really ought to try to agree. And they say, no, we didn't deliberately make it the same around the Higgs, and yet nevertheless it is. Of course, the other side of that is that if you go up here to the QQ bar, the concordance there isn't actually quite as good as it is for the gluon. It's starting to go off a little bit more. Now, we can see, though, that this is pretty good if you're going to work around the middling region, producing W's, Z's, Higgs. Let's go up a bit more. you produce not a top on its own usually, but a TT-bar pair. So that would come in at around 370 here. Also not too bad. Where it is getting bad is where you would expect new physics at high X. Now, to deal with this, the PDF community got together and decided to try to combine the results of those 3 PDFs, right? To try to come up with a PDF which was the best of all possible worlds. And that was done by a statistical combination. Replicas were taken of all of them, put together, and then re-averaged in order to try to come out with the best statistical combination. And here are just some comparisons of how well the outcoming PDF, which is called NNLOMC, agreed with the prior that you put in. And it was then condensed into 3 sets of slightly, see, MC900 means you'd have 900 replicas to deal with every time you wanted to make a calculation. Nobody wants to have to do the calculation 900 times. So these were compressed into sets with only 30, or for slightly more accuracy, 100 replicas. And this is just a comparison of how well those different things agree with each other. Now, there are 2, this is actually good. It's called the PDF for LHC PDF, and I would recommend it to you if you just want to get a good idea of, what's our best knowledge of things. But there are 2 criticisms of it. The statistical combination that was done of these PDFs didn't really account for the fact that there would in practice be correlations between them because they used the same data sets. For one thing, right? So it's bound to be that a fluctuation down in one is likely to be a fluctuation down in the other. Not completely, but we really want to redo this combination using correlation information. So far that has not been done. It is the step that the PDF for LHC group are doing right now throughout this year, trying to do it with correlations. But there's another objection to this, and that is that there are more than just the 3 PDFs that I have shown you here on the market of possible PDF extractions. So, just for amusement's sake, right, these 3 are not the only ones on the market. There is also the HERA PDF, and in this plot I have normalized the others to the HERA PDF, so you can see the deviations there are somewhat larger. That's QQ-bar and gluon as usual. Why might you want to use a PDF just from HERA? Well, the one main reason is it is guaranteed new physics free, right? This is done just by fitting the data to the deep inelastic scattering from HERA and evolving up. It doesn't contain any data from the collider itself, which means that you can't have sort of factored into your fitting the idea that new physics is there. Of course, the fact that you have, this is the main data set in all the PDF fits, but it does lack information in some kinematic corners. So the win is that it's new physics free, and the loss is that it can have larger uncertainties in some regions because it simply doesn't have as much information in all regions. The other plot I've put on here includes, along with NN PDF that it's normalized to, the PDFs from the ABM group. And I've put here what they like. They themselves like to use alpha S of 114, so this is what they like in blue, right? But this has been redone at 118 to try to get the best possible agreement with other people, so that's what that looks like in red. But it still differs to some extent. And this is a bit of an outsider. It uses a different heavy flavor scheme and so on than most of the others do. But if you talk to the authors of this PDF, they will absolutely stand up for you and tell you that they are the people who are right and the others are wrong. So, you can't ever be completely sure what is going on here. Now, okay, so I said about new physics at high X. I mean, why are we interested in the high X gluon, right? Why do we want to get it better? Because much of the interesting physics at the LHC is in fact gluon initiated. The top is, the Higgs is, and many beyond standard model processes, like the example on this page is gluon to gluino, supposing such supersymmetric gluons exist. Now, if I take just the high scale end of the plots I was showing, linear now, not log, so we're emphasizing that high end, right? And I plot the PDFs on it, gluon, luminosity and ratio, and I've put on everybody's PDFs here, so you can see that ABM one differing really quite extremely. That's because of its choice of value of alpha S. This has not been rejigged to 0.118. You can see how badly we know it. And the consequence of this is that if you try and say, what is this gluino-gluino cross-section, then in ratio to the central prediction here, you've got a spread of the gluino-gluino cross-section by, a factor of 2 or so. So knowing that whether you've really seen this or not is a matter of having a precise prediction and seeing that that's what you get, and we really don't have one at the moment. Another example is, it's also a problem at high X, even if you're not thinking of the gluon, but of the C, right? The Drell-Yan processes are some of the most obvious places where you might get new physics, right? Drell-Yan Q-cube-R-in is what makes the Z for us, but if there are higher mass Zs like Z primes, they will also appear in this process. If a Z prime, say, was at 3 TeV, we would find it there. You can also think of this in terms of contact interactions, right? A contact interaction like the original Fermi interaction, right? A new contact interaction might show up as a hardening of the spectrum. So here's the data to date from 13 TeV running. There happen to be 2 plots just because this has been done for dielectrons and dimuons in both channels, but the result is pretty much the same in both. This is as far as we've got, up to 2 TeV, and we're not seeing any sign of anything new. But this on the plot at the bottom, right, this is the actual data. This is the data in ratio, normalizing to 1 here and showing the data. And then we show the uncertainties on our predictions for this, and you can see it broadening out here at high scale, how well we don't know this, and that's completely due to the PDF uncertainty that we don't really know it. So if there really were a Z prime, it might indeed stand out like a sore thumb. But if it's just a matter of a new contact interaction, that just slightly changes the high X shape, and it's not clear you're going to really be able to tell that from a slight upward variation in your Parton distributions. And this is the problem. This is why you need to know them better. So also, as I said in the introduction, it's not just looking for high X physics where we have a problem. It's also trying to identify beyond standard model physics effects from precision observations. Now, it's become actually quite amazing to us, at least in Atlas, that we had been able to get a measurement from our data of the mass of the W with an uncertainty of plus or minus 19 MeV, right? The world average now is plus or minus 8 from a fit to all possible input datas, where quite a lot of the inputs have come from LEP, LEP being the E plus E minus collider, right? A much cleaner environment, an environment free of uncertainties on Parton distributions to some extent. We're almost doing as well as LEP did now in Atlas, right? In terms of how well we can measure the W mass. And we can measure the top mass as well, and when it comes to looking for beyond standard model physics, what we're looking for is some discrepancy where the intersections of the mass of the W and the mass of the top would not be coming exactly where the standard model said they would, right? That would be interesting. Now, we're not at the level of being able to say this yet. We want to get this better. We've got a whole load of new high luminosity running to look forward to when the collider's been upgraded, right? What would be stopping us getting this error down? It would be the uncertainty on the Parton distributions. And to show you that, I don't expect you to read every column, but this is just to impress you that getting this kind of mass on the W is not an easy job. These are all the channels that have been fitted for the W decay in various ways, in various rapidity regions, and the masses that came out of the fit. And you've got the statistical uncertainty on this here, right? And the total uncertainty there, and contributions, most of these contributions are from experimental systematics, but the last one is from the PDF uncertainty. And in every case, it's the PDF uncertainty that is the biggest one apart from the statistics. So as we improve, these statistical errors will go down, but we don't as yet see any, where is the hope for the Parton distribution uncertainty coming down? That's the problem. Another example of this kind of thing is a measurement of sine squared theta w. These are the world data on it, which at the moment the precision is dominated from the LEP and SLD measurements, right? It's very tight. CMS is starting to make measurements, as are we at Atlas, and again, we're not there at the ultimate precision yet, but we're hoping to get there. This plot kind of illustrates the problem about statistics versus PDF uncertainties visually for this. This is an error on sine squared theta effective. Right? Now, in the black, now it says nominal, and these are just two different rapidity regions, right? So whether it's clear, totally, what do I mean? Whether it's a full line or a dashed line is just a matter of where we put the rapidity cuts. The statistical errors are here for each of those rapidity graphs, assumed to be going down. As the luminosity of the new collider goes up, we get more and more statistics. This statistical error comes down. There's the current PDF error in blue. So the worst case scenario is, unfortunately, that does not go down, right? And in red is an attempt to see whether one could think of ways of getting it to come down, which is called the constrained rather than the nominal, right? And the way the constraint was done was that you say, well, maybe we could best improve the PDFs by using the actual data that we're using for the sine squared theta w measurement, using that data itself to improve the PDF. And what you would do is you would fit to Parton distributions at the same time as sine squared theta w, ideally. Now, we can't do that yet, we don't have the data, but an exercise was done of trying to refit, do a sine squared theta w fit for each of the PDF replicas of the NN PDF and weight them according to how well they seem to describe the overall data. So if you've got a good chi-squared, you'll get a high weight, and if you've got a bad chi-squared, you'll get a worse weight. And that changes the blue into the red. Okay, it's still, it's still worse than the statistical error, but it could be better. These are the kind of things that we're starting to think about right now, what to do, how to address this problem. And I think lastly on this theme, here are the various different projection channels for the Higgs through, gluon, vector boson fusion, W and H prediction, top and H prediction, and in each case you've got uncertainties from the choice of the scale, and you've got PDF uncertainties, and you can see that PDF uncertainties are really pretty significant. So, is there hope for the future? I mentioned a technique of trying to reweight to the data you're actually fitting, but the real hope would be to be able to improve matters by fitting high luminosity data itself. So this is the same plot I showed in one of my earlier talks about the extension of the HERA region into the LHC using data like jet data in the purple, Drell-Yan data on the W and the Z in the green, and so on. Right? And it's listed down here what extra processes you can put in other than deep inelastic scattering. So it's Drell-Yan, it's WZ rapidity distributions, it's jet PT spectra, TT bar distributions, and boson plus jet or heavy flavor. These are all now, hopefully going to contribute to matters. We've already begun. Some of it has already been done. The question is, how much better is it going to get? So let's see, like today, right? As of today, how much better has it got? These are plots from the NN PDF group where the green is their best answer and the red is if they had not put in any of those LHC data. Right? And in each case, this is a ratio to their best fit of the U valence. I think it's just the U quark. It's got U valence and C in it. So for the U quark, that's the ratio of putting in the LHC to not putting it in. Same for the D quark, same for the charm, same for the gluon. So you can see that In some cases, the uncertainty has certainly decreased. In some cases, not putting in the LHC or putting it in has made even a difference to the shape, for example, of the gluon, right? And in case of the charm, this is quite extreme, but the charm and the gluon are intimately tied to each other anyway. The charm is being generated from the gluon, so that's not a surprise. So that's the sort of overall message of how well we're doing today. Unfortunately, it's still not really quite good enough, but okay, these data make a difference. We could look at some separate data sets. Like this was sort of every data set you can think of, all of these data sets at once. You could try and break it up a bit into sets which affect the gluon, and that would be the PT distribution of the Z, it would be the TT bar differential distributions, it would be jet PT spectra. Now, this again is their best answer, and that answer leaving out a particular data set, leaving out the jets, leaving out the top, leaving out the ZPT. You can see these in some cases pull in different directions, right? Without the top it goes up, without the jets it tends to go down more, right? So there's a lot of data sets going into this, but I would just issue a health warning, which is what they have done to do this is choose particular sets of the differential distributions. They haven't put in all the top differential distributions that we have. They've put in just the rapidity distributions, and the reason was because there were no correlation matrices given to the other spectra. You can't determine, say, the mass of the TT bar pair and then determine the rapidity of the TT bar pair on the very same data and put them both in the fit without accounting for the fact that these will be correlated, right? It couldn't be done because we experimentalists at this stage had let them down by not giving them the covariance matrices, right? This has been done since, but the PDF analysis has not been redone afterwards, right? It's the same story with the jets, and it's a slightly worse story with the jets because the CMS jets are in there, and in case of the Atlas jets, only one of the rapidity ranges is in there, and the reason that the others aren't in there is because the chi-squareds weren't very good. And actually, that is not a good reason for leaving out a data set, right? Just because you don't like it, you don't like the result that came out. So, again, this is about as good as we can do, but take it with a little bit of salt because, you know, not everything is being done in a perfect way. And other PDF groups could make other choices about what they would and wouldn't put in. The other groups haven't yet updated to this state of the art of having this much LHC data in, so we can't really compare. But they are doing it right now, right? There's going to be a CT18. Curious that CT18, right? They're going to issue it in 2019, they say, but they've been calling it CT18 for a year now and they haven't published it yet. So I keep saying, why don't you just call it CT19? And they say, no, too confusing. But, okay. I also asked MMHT if there would be an MMHT19, and they said, first of all, it can't be MMHT because two of our authors left. And secondly, I'm not sure it's going to be 19 at all, it might be 20. So anyway, carrying on with this. Yes, those were the data sets which affected the gluon. Here we've got some data sets which affect the quarks. That's mostly the W and Z production data. And here you've got it adding in with LHCb or not doing so, with the U quark ratio and the D quark ratio. You can see LHCb itself makes a difference at high X. That's because LHCb's kinematic region looks at higher rapidity. And over here, it's having in or not having in some Atlas WZ data that has made a difference in shape. So you say, okay, well, in general, things are improving. Will this rate of improvement keep on happening? I mean, happily, you would hope that it would. But the answer is it's not so obvious that this will keep improving at this level because of the rate of precision you actually require to improve. And I want to explain this with a very simple example, right? What these are plots of it's a plot of the ratio of the strange quark to the down type quark in the C, essentially, and it's got on it the old-fashioned assumption we used to have that it was suppressed by a factor of 2, so at 0.5. And it's also got on some more modern analyses that come from the Atlas collaboration using WZ data and W plus charm data. But the point here is this is what it looks like at low scale, and this is what it looks like at high scale. As you go from low to high scale, gluons are splitting to strange anti-strange pairs, and there are going to be more strange anti-strange at, at low X because of that. This is the difference between the green there and the green there is QCD evolution, right? If, however, you start where you've already got equality of all the flavors, you will continue to have equality of all the flavors because the glue splitting to Q bar blind will just maintain the ratio unity. But the real point of this is to look at these little error bars I've put on. If you can make a measurement at low scale here, right, and you're making a measurement of, say, I mean, this is hypothetical, it's just 10% accuracy. We can do better than that. But a 10% measurement at low scale is here. And it would certainly tell you if you were there or you were there. But a 10% measurement at high scale is actually this big. Look at the difference in scales on the plots, because as you evolve, the actual level of uncertainty gets smaller and smaller and smaller, because it's essentially now just QCD and not your assumptions that are determining the uncertainty, right? But correspondingly, if you want to tell that from that, you've got to be able to make a more accurate measurement, because if your measurement now looks like this is still 10%, it's not really clear that it's ruling out that. It's only 2 standard deviations away. That's not an immense deal, right? It was more like 4 standard deviations up there. So what this is actually telling us is if you're working at high scale, trying to tell PDFs at high scale, you've got to make much more accurate measurements because things are already fairly tight from the QCD. So if you want to tell one thing from another, you'd better measure it accurately. So just how precise can we possibly be? We think in Atlas that we've already made just about the most precise measurement that one could ever hope to make. These were the inclusive W and Z differential distributions, and the level of accuracy is at sub-percent level in the W from 0.6 to 1%, for the Zs according to where they are in rapidity 0.4%, or going out to forward rapidity 2.3%, and a luminosity uncertainty of 1.8. The other information on this slide tells you how much of these overall uncertainties came from particular experimental uncertainties. Only interesting to you if you're an experimentalist and you wonder how well you're doing. But we really are unlikely to be able to beat this, even if we have got a nice upgraded high luminosity LHC, because the change in the kinematic region going up from 7 or 8 TeV to 13 or 14 doesn't really change your probed region very much. And basically, these errors were not limited by the statistics at all. They're completely systematic dominated. So it doesn't matter how much you increase your statistics, it's not going to get better, because getting better than 1% on your systematic errors is really, really tough. It took about 5 years to get this out from when the data were actually shot, right? It took that long to really assess the systematic errors. I don't know if anybody in the room is an experimentalist, but this really is the state of the art. If you want to be that precise, it's very difficult. So it looks like this is as good as it gets for this process. So the question we want to ask is, for what processes could we in fact do better? You know, where should we measure in order to do better? What should we measure? I'll just briefly highlight the theoretical and experimental challenges in this. The W and Z production and Drell-Yan distributions, right, are sensitive to valence quarks, to strangeness, even to the photon content that's in the proton, right? But we're only going to, I think, get some modest improvement at the edges of phase space. And when we get that modest improvement experimentally, we'll have to face the need for log 1 by X resummation, which I spoke about theoretically we'll have to face that, which I spoke about in the morning lecture. The off-peak Drell-Yan, right, can still improve somewhat. It's on the Z peak we really have the fantastic measurement. But the low-massed off-peak Drell-Yan will bring the same kind of low X challenges as the regular Drell-Yan, and the high-mass Drell-Yan requires fantastic understanding of electroweak corrections and the photon content of the proton itself. Jet distributions, inclusive dijet and trijet, I think that these do hold a hope for really improving, that we can improve on that because we've not got the best measurements we could as yet. The data itself, I think, needs to be better understood. We have to work harder on systematic uncertainties for that. The top anti-top distributions are also sensitive to the gluon. We've even got the next to leading order calculations available. But if you look at the data that we have at the moment, there are inconsistencies between the two experiments, CMS and ATLAS, and there are even inconsistencies between different TT-bar spectra within one experiment. So there are definite questions again about the treatment of systematics. What this really means is it's not a perfect world. In a perfect world, you would do this measurement, you would get the information. In an imperfect world, you find that you're struggling to understand the experiment, essentially, the systematic uncertainties on it. And another hope for improvement is to combine different types of data at different beam energies, right, and account for the correlations between them. This is being realized more and more now, that when we do, the way it tends to happen at an experiment like ATLAS is one team will be doing W and Z production at 7 TeV, and a completely different team will do it at 8 TeV, and they might make totally different choices about exactly how they cut and manipulate the data. And then when it comes out, you can't assess the correlations because things haven't been done in the same way. So more and more it's being realized that you have to have more coherence across what we're doing at different beam energies so that we can correlate things, and then we might really be getting somewhere. So I was just going to talk about some recent work that had been done trying to study potential improvements using these very processes I've been talking about, like Drell-Yan production, TT-bar production, jet production, and so on, and trying to assess what will happen when we've got the high luminosity LHC. So they have to generate pseudo data. They generate 3 inverse attobarns of data for CMS and ATLAS, and a corresponding 0.3 inverse attobarn for LHCb. That's a sort of realistic ratio of how much of the data each of these experiments take, right? And they then make pessimistic and optimistic assumptions about how good systematics could ever be based on experience with real data by talking to experimentalists, right? And they make assumptions about possible improvement due to knowing correlations. Pessimistic is there'll be no improvement. Optimistic is it might fall by a factor of 4 to 0.25. And also about possible, not just about correlations, but about actual reduction in uncertainty. Pessimistic, again, there won't be any reduction. Optimistic, we might get it reduced down to 40% of what it currently is. And this is about as good as you can possibly do with pseudo data, but let's not forget that that's an ideal situation. It doesn't have the problems of real data. This is just a table of all the processes they put in, what were the kinematic regions they considered, the number of different data sets they had, and these pessimistic and optimistic assumptions about the reduction in error due to knowledge of correlations and decrease in systematics. And this is a very technical slide. I'm not really expecting you to read it. It's just to say, what do you actually do when you've got these pseudo data? Like, you already will have a PDF set and its errors. What you do is you take your pseudo data with its with its predicted experimental cross-section and its statistical and systematic errors and the correlated systematic errors, and you assume that each experimental error correlated can all be shifted one way up or one way down. And then you do the same thing with the theory. You've got theory from a PDF. That PDF has several replicas or eigenvectors, and you consider shifting each one up and down, and you see like what the overall quality of fit is. And as you do that, right, the data itself will say, well, actually, I didn't really like your central PDF. What I liked was when you shifted it a bit into replica number 35 or whatever, right? Replica 35 looks better to me, or, you know, to some extent which you quantify with this chi-squared, and replica number 24 looks worse. So again, what you're doing is you reweight the data according to how well the replicas are described. Sorry, you reweight the PDF according to how well its replicas are describing the pseudo data, and you then come out with new PDFs, new replicas, where you're taking into account what the pseudo data said about what they liked or didn't like. That's the technique. Here's the bottom line, right? So, in green is the PDF for LHC as it is today, and in red is adding this high luminosity pseudo data, scenario A and scenario C, where scenario A is being pessimistic about systematics and scenario C is being optimistic. It turns out when we look at this, this is the ratio of the gluons, the D, that's the strangeness ratio, this is the U-bar. It turns out it hasn't made much difference what we assumed about systematics. That's because we did this on processes which are still today statistics limited, right? That's why they're improving. Today they are statistics limited, so it's mostly the decrease in statistics that is getting us an improvement here. And I now present this in terms of the Parton luminosities. So this is gluon, quark, anti-quark, quark, quark, and quark gluon luminosities. If we take the baseline of what we have today as being unity, this is how much better it will get with our optimistic situation in blue and our pessimistic situation in red. So it's quite impressive. Things are falling by and large by a factor of about 2, right? Falling to about 0.5 or so. Exactly where they're falling depends upon the process and the kinematics, so it does differ across the mass of the object that you're producing. And another way to see this is if we look at particular cross-sections, like that gluino pair production cross-section I showed earlier. Today, uncertainty this big, improvement, it's decreased. Here's the dijet production, really quite an impressive improvement. And here's the Higgs to BB bar, again, quite an impressive improvement, right? So, this is looking quite good. Admittedly, sometimes when you look at this gluino one, you say, okay, fair enough, but it's still a bit, you know, it's still rather unknown, isn't it? It's still not great. So my last sort of theme on this is, can we do even better than what the high luminosity LHC is going to give us, right? And possibly we can, but it depends upon having a new machine, right? You might know that there is a proposal at the LHC to build an LHeC. What that means is building a new ring to fire electrons in to hit the protons, so that you've got a high energy EP machine, a new deep inelastic scattering machine at the LHC itself. There's even a further future version of this. You might also know that one of the proposals for future colliders is a future circular collider in the Geneva region. And if we can, there's Lake Geneva at the end, and here's the current facilities, and here's the proposal for how much bigger it would be with an FCC, right? I see Andre shaking his head, and I'm also inclined to believe this will never happen, but it is at least a proposal on the table. And then if you were going to do that with hadron-hadron, you can equally well do it with electron-hadron. But I'll concentrate most on the LHeC just for the last few slides, because that is at least a bit more realistic that you could do it, and it's vastly cheaper as well. So, this is just a slide, summarizing lepton-proton facilities. This is in terms of the kinematic plane. This is the centre of mass energy of the collider. This is its luminosity. We had HERA here, which has really quite a high centre of mass energy, but a low luminosity. We have the older data here with lower energies. There are proposals out for what's called an EIC in the States, an electron-ion collider, and most of the physics reasons for that is investigating the heavy ions, which are more dense than protons, and whereby some of that physics I was talking about in the last lecture in the morning of high density might come in. That's the main reason for doing this, and that would sit at not quite as high an energy as HERA, but with much more luminosity. So here's the proposed LHeC, again, higher energy, higher luminosity, and the proposed FCC-EP option. And this is just a plot of, like, over the years, something like, you know, since 1960, how much deeper have we managed to probe inside the protons from the earliest experiments at SLAC, where we could actually, you know, identify proton scattering, through the Fermilab, the CERN experiments, HERA, and now into the future, probing deeper and deeper. Now, this is just a plot of the kinematic plane again. There's the LHC, there's HERA, you've seen it before. The LHeC would come here, and it would bridge the gap from one to the other. So we would have better information from deep inelastic scattering to evolve up to the LHC, because we'd have much broader coverage. And one of the issues I already referred to about the LHC is that realistically, when you're using LHC data, you actually have to combine many different data sets that are analyzed by different groups with different procedures. And so the evaluation of systematic uncertainties and cross-correlating them is actually quite difficult. If we ran an LHeC, the nature of those experiments is such that the whole plane would be analysed by the same people completely coherently. So you would stand a better chance of understanding that. So it represents an increase in the kinematic reach, so tremendous potential for an increase in precision of Parton distribution functions. It also accesses a new kinematic region at low X, where we might learn more about those regions of QCD I spoke about in the fourth lecture, where you might have gluon saturation. And furthermore, just, you know, I think I already gave this motivation before, these precision PDFs are needed for beyond standard model physics. I'm not going to spend much time on this page. This is just a description of how the LHeC pseudo-data predictions have been obtained. This is a deep inelastic scattering experiment, so you've already seen all this stuff about how that determines the partons. The new information here is what energies of electron and proton are we considering, what polarizations of them, what luminosities, and what are we assuming about the systematic errors that we could achieve on the basis of past experience. One analysis that was done on this was to therefore generate LHeC pseudo-data and add it to today's data, where today's data had in it the HERA final combined data, but also some data from Atlas and CMS and in various processes. And so you have, here's the ratio of U bar today to U bar today plus the LHeC. There's today, and there's what you would get with this LHeC pseudo-data. It's considerably more impressive than what we saw from the HL-LHC, right? Here it is for the gluon, and again, it's more impressive. It's still not wonderful, though, because frankly, the gluon is the difficult one, right? Pinning the gluon down is always the hardest thing to do. Now, just to make this actually a little bit more to compare it back to what we had with the HL-LHC, a rather similar exercise has been done using the LHeC pseudo-data and using it to profile the PDFs, just like we did with the HL-LHC data. So here are the luminosity plots again, gluon, gluon, quark, 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 anti-quark, and so on. And on it we have the HL-LHC improvement that we saw before in blue, and then an improvement by using the LHeC. So in each case, compare the high luminosity LHC to the LHEC. The LHEC is in general doing better. Exactly how much better depends upon the kinematic region and what you're interested in. At low X, it definitely does better. Sometimes at high X, it doesn't, but other times it definitely does. Clearly, what would actually be nice would be to have both. So close to my final slide here, right, I add on to those previous plots actually having both an LHEC and the high luminosity LHC. That's in purple at the bottom. So we're finally getting down to uncertainties around about, what, 0.1 to 0.2 of what we've currently got. That would be great if we ever got there. Okay, 5 minutes. I also will just mention as a last topic, the LHEC would also improve how well we can possibly know alpha S, right? This is the usual plot about unification of couplings, or rather, the lack of complete unification of them at the gut scale, right? And there's your fine structure constant, your weak coupling, your alpha S. The red is today's error on alpha S. The black is a mock-up of what we think the LHEC could achieve in terms of precision. And so if you're that precise, you can certainly tell that you're not really meeting, right? Whereas with a slop like the red slop, well, maybe there's some room for maneuver there. So, put it there, right. Yes, we think that we could actually go down to an almost, a sub% error on alpha S, more like 0.1%. And just to see that in comparison to what I showed this morning, this is a curve from the LHEC conceptual design report about possible errors on alpha S. But I'm going to take it over here. It's a 0.3% precision, right? And compare it to what I showed this morning, where we had only HERA-inclusive data, HERA-inclusive plus jets, and on the absolute same scale for the variation of alpha S. That's what this new measurement would be, right? So if we can do it, astoundingly impressive. So I think I've come to the end here, and the summary is just this, that we need precision Parton distributions for beyond standard model physics. The measurements we're going to get from the high luminosity LHC are certainly going to improve on our current knowledge, but a dedicated deep inelastic scattering machine like the LHEC could do better, and better in terms of alpha S. And the reduction in alpha S and the PDF uncertainty will absolutely reduce the remaining uncertainties on the Higgs cross-section. And finally, an LHEC would allow the exploration of a kinematic regime at low X, where we would learn probably more about QCD itself, because we'd be in a region that we've barely explored so far, into the, BFKL and the nonlinear regions. So, but to talk about that in any detail is a completely different talk, and we're nearly 5:30, so I think that's it.
Questions, please.
Yes.
How about
How about
a linear collider rather than circular ones?
a what?
Linear colliders rather than circular colliders.
But what do you want to collide linearly? Which particles?
Protons.
Yeah, okay, so what, for the LHEC, they did consider both a ring of electrons and a linear electron collider colliding with the protons. But of course, one of the options for the future is not a hadron-hadron circular collider, it is the ILC, right, International Linear Collider. It's good you asked me what about it. There are meetings about future strategy going on all over the world at the moment. We had all hoped that the Japanese might commit to that at around about New Year time, but they didn't actually commit. They hedged a bit. And we've had a European strategy meeting quite recently saying, what do we think? Now, obviously the European option, the main one, is that future circular collider, but do we really think they're going to build another one in CERN? I mean, I'm more inclined to think that it might be it might be in China, in Japan, where something future might come. And certainly, as you've just said, it being a linear collider is one of the options that are being explored. There's also, I forgot to mention it, the CLIC proposal for a linear collider at CERN as well. So all of this is up in the air now. You will live to see it. I'm not sure I will, so. Sorry, yes.
This may be a little too far-fetched, but can you learn anything about the particle distribution functions from other sources of protons, say cosmic rays and other kinds of experiments?
Well. Right now, today, I think I'd say that was the other way around, in that, knowing what parton distribution functions are like is helping us in understanding some of the more astrophysical observations like the high-energy neutrino cross-sections. But do you want to comment on that, Samir? You don't?
Well, yeah, it's right. And cosmic rays, you have energies going up to 1 million times higher than you'll ever get in any machine on Earth. So in principle, you could access kinematic regions in elastic scattering that you can't ever do. But with the highest energy we have measured so far is about 10 TeV, which is 10,000 TeV. And that is consistent with the standard model. So it's actually, we have verified standard model up to 10,000 TeV. Not many people know this, at least in this sector. But in principle, there are cosmic rays going up to 10 to the 10 GeV. And if we can probe the elastic scattering there, if we detect those neutrinos, this will be done by a proposal called IceCube Gen 2. Then, in principle, we can prove some of these things that she mentioned. At low X, you can have formation perhaps of new phases of QCD, like colored glass condensate and so on. We will be able to do that. But that's problem there is the event rate is very low. Cosmic rays are very rare, and you don't control them. But they are for free. So that is something which people are getting quite excited about. Astroparticle experiments doing fundamental physics.
I wanted to ask a question about LHeC.
Yes.
If I understand correctly, at the moment there are still two proposals, one from JLab and one from...
Oh, you mean EIC?
Yes,
yeah,
EIC,
right, yeah.
Yes. I just wonder which property, and they have slightly different sort of set of parameters in both proposals. So for PDFs, what are the most important characteristics of the accelerator that you would like to see? Is it luminosity? What are the...
Yes, the luminosity would be for us a crucial parameter, I think, because they won't just run on ions, they will run on protons, and we're in a similar kinematic region to HERA, but with more luminosity. So we could probably do things we'd not been able to do, like you can't really probe at HERA very well strange quarks, for example, because you just don't have enough luminosity for the charge currents which would access them. At an EIC, I guess we would have that. Now, I wouldn't like to decide between the JLab and the Brookhaven proposals on that basis, though, and they also seem to be keeping those two options open for a very long time. There's clearly a lot of political stuff going on there that they don't want to commit themselves, and some of my friends from there, they said, we've really got to get this decision this year, because next year the government won't want to do anything, because they'll be campaigning for the 2020 elections again by then, and like everything will just get shelved until after that. So not good news, I think. And today's the 4th of July, isn't it? Yes.
So, if no other questions, let us thank this.